I mean, we're still kind of in the learning phase. We certainly know that we have been able to expand the footprint of said copper deposits, and we know they're really big. We're still learning really exactly how to predict them, although there are we definitely use predictions. So I kind of like to start our talk off with a question or a statement about why bother standing up and giving the talk. And in this case, I guess it really comes down to this. Do we have the guts to put our assumed mineral systems understanding in sediment-hosted copper to the ultimate test and look for something new under completely transported cover where you walk across the ground and don't see anything? So this is kind of like Tony led off his talk. This is now the real world of exploration. Cam pointed out first thing this morning that we always start at the deposit scale and we work our way outwards and we build up our body of knowledge about why the deposit was there, and it has to be like that. But then when you actually go exploring, you're starting at the opposite end, and you're starting here, and you've got nothing, and you don't know if you're going to find something. You have to work your way down to maybe find a couple of square kilometers where hopefully you can make some money. This is what we've had to do, and we've decided to do, and it takes. I guess it's a good test of science, and it's a good test of corporate and management faith, and a certain amount of staying power. We're going to take the lessons from the African Copperbelt, and that's where First Quantum grew up, really, and everything we know from the African Copperbelt, and I'll go through some of these lessons that we've learned about different ingredients in a mineral systems model, and then the proxies we use for mapping these ingredients. Then move off out to the bigger picture, the big cracks lead to big deposits type of thinking, and how we use that to target ourselves into a new part of the world, being northwest Botswana. Then when we actually get there and have a project area, many thousand square kilometers, what do you do first? I'm a geophysicist, but you don't have to be a geophysicist, and it's not a bias that obviously when you're looking at something like the photo I showed, you're going to put some of your exploration dollars into collecting geophysical data sets to see underneath the surface. So in the talk here, I'm kind of mixing together mineral systems exploration and undercover exploration, because I guess undercover exploration is the ultimate test of if mineral systems is working. And then the all-important geochemical layer, we're talking about anywhere from about 30 to 100 plus meters of Kalahari sands over top of the rocks we really want to see. How are we going to get the geochemical data? We're doing it a very expensive and slow way, because we really don't know what we actually have to do. So we're trying to test everything. So we're diamond drilling for soil samples. Are we there yet? Well, as a preview, I don't have the prize at the end of the talk to show you. It's kind of a story in progress. If that sounds like a cop-out, maybe it is, but actually the story is, like I say, never let the facts get in the way of a good story. So the story is really about how the process we're going through in the mineral systems environment to actually get down to our target, and a slide of general conclusions. So here's where we are. I'll use the mouse so everyone can see. As I said, this is where First Quantum grew up in the African Copperbelt. It straddles Zambia and the DRC. And we're trying to learn everything. We take everything we learned there over the last 5 years or so, and port it down here to the south, northwest Botswana. Just to point out, this is not Botswana. This is not the Kalahari Copperbelt where Discovery Metals and some other companies have had some success. They are more down here, and we're up right in the northwest corner here. So it's a different geological part of Botswana. So the lessons from our work in Zambia. So the copper source is a combination probably of red beds and basement, and maybe as deep as mafic crust underplating. In the end, as an exploration team, we actually don't really have to care where the copper comes from in the Copperbelt, because we've learned there's just that much of it around there. That all we have to really worry about in exploring is where it ends up. But generally, the copper source is hematitic red beds. that have been scavenged by oxidized basin brines, very hypersaline brines, for quite a long time, circulating in the basin. And it is really a long time. I mean, the start of basin extension up here in Zambia, in the Katangan, was about 880 million years ago. And peak metamorphism, probably a relatively mild compressional event, was at about 550 MA, when most of the copper deposits were formed. So that's 300, up to 300 million years of the basin forming, extending, and brines circulating, and being able to scavenge the copper. And so evaporites play a big role here in actually, providing the source of the salinity. And so you'll see a lot of the elements in this story are very similar to what Ian was talking about in text lead zinc exploration. For obvious reasons, there's just maybe slight differences in temperature and fluid composition and stuff. Then there's a switch from extension compression, so the favorable geodynamic, transient geodynamics that we've heard about. And it's not, it's not a very big kind of compressional event, we don't think. But that trigger, that change in tectonic regime is very closely associated with the timing of all the, of most of the copper deposits. That said, there is some diagenetic copper mineralization in the classic Copperbelt that's earlier. And then these oxidized fluids are going to travel through some kind of structural or porous pathway. So we have deposits in the Copperbelt which are very definitely structurally controlled, vein-hosted, but they still have an association with stratigraphy, with favorable stratigraphy. And but there's got to be, stratigraphy is very laterally extensive. There's got to be ways to actually focus these fluids in specific areas. And then the copper and other associated minerals like nickel and uranium drop out at redox boundaries. And I've written here the first boundary encountered above the basement or above the source region, because it's conceivable that if there's a favorable and rapid structural pathway to bypass a lowermost reductant, these oxidized copper-bearing fluids could find themselves higher up in the stratigraphy and encounter another reducing environment and drop out there. So that's not something to be discounted. And then we've learned that the footprint of mineralization is very large. And this is the actual mineral footprint. The alteration footprint is going to be even bigger, but that's something that's not been really well documented. Certainly we don't have that information to hand. But the footprint is very large. Just on that note, let's look at some of these footprints. So the very largest, Lubin here, is in the Kupferschiefer in Poland. Very huge deposit, very large extent. Here's the scale bar down below. You see the 10 kilometers like this. So this is actually about a kilometer and a half more underground. Very thin, very, very high grade, discovered by, I believe, grid drilling, 2-kilometer holes or something. So very expensive, not for everyone's exploration strategy. These deposits that are in black are shale-hosted, in situ reducing units. The pinkish deposits are sandstone-hosted, and there's probably a different mechanism for the reduction trap. Some of these that are striped, like Kansanshi here and Lanchi and Frontier, are stratigraphically associated, but vein-hosted, very definitely structurally controlled and vein-hosted. Kamoa is in the DRC, is in the conglomerate. And here, just for size comparison, we've got Pebble, a very well-known and very large porphyry copper deposit, with footprints that's kind of small compared to some of the bigger copper deposits. So this is where I point. This is where the African Copperbelt is, called the Lefilian Arc. And these are some of the mines. Kalumbila, Kansanshi, Frontier, Lanchi are first quantum mines. The one is currently a barrack mine, and Kamoa is Ivanhoe ironclads. And these are some of the deposits where we've gained a lot of our knowledge from. So a very kind of generic basin diagram that shows most of the ingredients that we need, that we're looking for. So we've got a metal source down here in the red beds where the copper has been stripping, the brines been stripping copper. Perhaps some metal sources, mafic units in the basement, or even further down, maybe the brines flow down, are drawn down the faults and back up sometimes. But basically we have this thick sequence of evaporites, which is an important prerequisite for choosing prospective basins, from which the brines are derived, and being heavy, as Ian mentioned, they sink down. They spend a lot of time circulating down in the red bed, scavenge the copper. There's a favorable transient geodynamics and a change in the stress regime, and the fluids are pumped back up, and they may drop out here in this layer, sandstones and siltstones, but there's shales and stuff there. They may drop out at a reducing horizon here, relative redox boundary. They may go higher up, as I said, and find themselves dropping out at another redox boundary. A closer look at the redox trap. It's basically a chemical trap where we've got the red beds down below, the fluids coming up, hitting this redox boundary, which in a lot of cases is in situ shale horizon. It can also be carbonates. It can also be conglomerates with some organic material. And this is the interesting thing. So this sulfur, in the in situ case, will be in the shales, in the graphitic shales themselves. But the other possibility that pertains to these arenite-hosted sandstone deposits, is sandstone-hosted copper deposits, is that this comes actually from what we call mobile hydrocarbons. So basically sour gas, H2S. And that's a more complicated thing to look for, at least undercover, because it doesn't, obviously shales, graphitic shales, most people know are quite conductive, so this gives you something to look for from the surface. But these arenite-hosted deposits, where it's basically like a failed petroleum system, so you're going to maybe a favorable structural trap, and the sour gas that used to be there, that acted as a reducing horizon for the copper brines, but is maybe no longer apparent. Just to illustrate the diverse stratigraphic settings for the deposits in Zambia and the DRC, here in the Zambian classic copperbelt is where everything started, and 100 years of mining, and some of the big well-known deposits, Konkola, Mufulira, Chingola, all the big names are here. And in fact, they're in this thing called the ore shale, which is the lowermost reducing horizon above the basement and the source plastic rocks here. Now, up higher in the column, these are two X-first quantum lines. Basically what has happened is that this stratigraphy is missing. So the source, the copper brines were able to go up higher, and these are two structurally controlled deposits. They go up higher and they deposit out here in much higher strata, and that's something that's relatively new in exploration, compared to a century of exploration in Zambia, looking outside of the traditional ore shale, for reasons that I've just said, because the ore shale is not there. So I won't spend too much more time. Kamoa is a more recent discovery by Ivanplatz in the DRC. Again, same thing, demonstrated that you've gone out of the traditional stratigraphy into something that's a very high level, but when you look at it actually in context of the source fluids areas and stuff, it has the same kind of relationship as being the first relative redox boundary above the oxidizing source. So empirically now, basement domes, deposits clustered here in the traditional copper belt in Zambia, right around the edges of basement domes. And as I said, this is called the ore shale, and so people spent decades and decades mapping, looking for more of the ore shale with good reason, and lots of stuff was found. One thing I want to point out here, so just on an empirical relationship, an association with basement domes is good. The other thing is, there's no reason why we can't have copper deposits many kilometers down in favorable stratigraphy, but these basement domes, in a practical sense, act to bring copper deposits to within economic reach of the surface. And so a lot of these, well, a few of these basement domes are cored by granites, so we can see them, we can map them on the surface at the Mwana and China granite here. Now the implication of that is that the granites are lower density than the surrounding basin sediments, and so you should get a gravity anomaly, and indeed you do when you look at the 1 to million scale geological map of Zambia here. You've got all these basement domes, which are generally gneiss, ortho-gneiss. And if you look over here, they all are associated with gravity lows. So they're less dense than the surrounding basin sediments and whatever basin is around here. So the inference is that not only do we see some basement domes cored by granites, but they probably all are at some level, hence giving this density contrast. And the petrophysics we've done has shown that the contrast between the granites, which are around 264, 265 grams per cc, and the basin sediments, which are generally quite heavy, like carbonates and hematitic sandstones and stuff, at about 2.8, well, you're approaching at least 2/3 of the density contrast that you get in granite greenstone terrain, where everyone knows that gravity mapping is a great tool. So it's really quite good. And so obviously this is something we've used to go and target hidden basement domes like these. I don't know if something's there, but that's the inference of this. Mapping redox boundaries with electromagnetic methods like AMT. Here's a section we did as a control line in the frontier deposit, right very close to the border between Zambia and the DRC. A bit over here, basement actually crops up to surface, so we started the line over here. We indeed mapped resistant basement. We had our drilling here. We indeed went through this Mwasha shale, very conductive. So that part is tied down. And so when we look at this section, what we're interpreting here is the resistant basement coming up here, not quite to surface, so hidden basement highs. I say domes, but because they look like domes on the maps, but they could be horsts, domes, just something that brings the basement up to close to surface. And so it's looking like it's doing a very good job at mapping the shales, being in this position, the first reducing horizon above the basement. And we were quite pleased with this, so we sent the team, see this section up here is the same as this little piece down here. And we sent the MT teams big lines out into the forest, 40 kilometers of mapping, with the intent here of finding these hidden basement domes. First Quantum came to had a rather sudden exit from the DRC, and so this was never tested, but what would have happened here is that our regional soil grids would have been placed over these hidden basement domes. Rather than trying to soil grid 40 by 40 kilometers, we'd go and focus on top of these basement domes. So these are still out here, and that's the reason there are no coordinates on this section. Okay, moving on to soil geochem. So this is from the Trident project in northwest Zambia. And what we have here from the soil, so we covered the whole thing with a grid of 300 by 300 meter soil sampling with full 4-acid multi-element assays. Subsequently, 300 by 300 was overkill in terms of the density, but it did allow us to do some really good studies. We could have gotten away with double that easily. So here we see very obvious dichotomy, zonation. We've got arsenic and arsenic and moly representing. They're very mobile elements, and they've been stripped from this the basement and basal sections here and deposited in higher stratigraphy. So this boundary here that actually comes up here, following along this, is actually a very well defined stratigraphic boundary between lower oxidized units and everything at the reducing unit and above. Same thing with moly. Another picture of mapping, a proxy again for mapping talc alteration. So we've seen this talc alteration along this stratigraphic horizon here, right? And the magnesium to aluminum ratio maps it very, very nicely. So this is pretty accurate. It picks up this contact between the basement and the overlying basal units and this basal shear zone, and then the higher strat above. So what we're mapping here basically is the redox boundary via geochem, and we're mapping what's left after the passage of this saline brine. You could also expect potassium and sodic alteration, and we looked at it. It doesn't give the same kind of precise picture, and maybe it's not actually that useful. Maybe it's an indication of very regional, large-scale, saline convection cells, fluid flow movement, but maybe it doesn't actually target you that well right into kind of smaller zones. Is someone going to tell me when I have 10 minutes? Okay. Mapping, okay, I have to read. Mapping the source and trap now with geochem. So here's a geological map, same area, without going into too much detail about the units. The pinky stuff here is the basement, orthogneiss, granitic gneiss. We've got the basal silicic plastic units here, and then we've got our right here is the phyllite that hosts the Sentinel deposit. It's in a very weird structural position that actually appears to be lower than this strat. But in fact, what's happened as far as our current models, it's dropped. It's a graben, a small graben. It's dropped actually to below its current its original stratigraphic level. And everything above here is high-level sediments, the high-level strat, right? And map gappers. So now that's pretty faint on my screen. Let's do that. It's a picture of normalized copper. You know what? I want you to see this, so I'm going to edit it on the fly. There we go. Okay. So it's not supposed to be faded out, but anyways, normalized copper. So what you see is that in the blue, this is all lower than background copper. So all this in these basement and basal sediments has been stripped of copper. You can see this boundary that I was pointing out before. This is background, and this is where it's been deposited. So here, with just the copper in soils, what you're mapping this large-scale stripping of copper from the source rocks and deposition in this localized environment. It's maybe it's always fun to open up cans of worms. Maybe it's a bit like Ross's model of the gold deposits, where you actually have a very local, high-level source of copper, and you can see it being stripped here and deposited somewhere else. So just a quick calculation. So we have about 50 square kilometers at 500 meters thickness of these basal siliciclastics, which at 10 ppm background copper gives us 30 million tons of copper that have been stripped away. The Sentinel deposit is 5 million tons. So part of our exploration effort on this package was to see if, well, maybe some of that, the missing 25 million tons is somewhere else. I think we've done a pretty good job of sterilizing the project. On the other hand, maybe that's I'm just thinking of this today about what is the efficiency of concentrating background copper into your deposit. Maybe 5 on 30 is good. I'm not sure. Something for discussion. Okay. So going out to the wider view now, where we started and where we're going, I'll have to skip very quickly. We use some very large scale data sets. Most of them are all free here, except for the blue one. We subscribe philosophically and financially to Graham Begg's GLAM project, which is mapping the basic lithospheric building blocks. So the big cracks map. These are some of Graham's boundaries in gray. Some of the things we drew based on the satellite gravity, the DTM, Landsat, everything. Looking for what we took as large-scale factors in the Copperbelt here. And basically, to go fast, it pointed us to these two target zones, 1 and 2, which happen to be in northwest Botswana. Now, in the interest of full disclosure and the full story, at this time, this was targeted independently. Then we got a phone call from Murray Hitzman, that we work a lot with in Copperbelt, and he's a director, he's junior, that was drilling for iron ore in northwest Botswana. And he phoned us and he said, guys, these people are drilling for iron ore, but they're drilling through all the same stratigraphy that you guys are drilling in northwest Zambia. So we went to look, and indeed it was very much the same. Talc kyanite alteration in the what we think is the Mwasha shale equivalent. At the moment, the only thing that's missing is a lot more of this stuff. So we also think we're in a bit higher level stratigraphy, which is the Mwasha equivalent. What do we do? Geophysics first, right? When you see this picture. So some of the lessons that I talked about is the basement being less dense than the basin sediments. So basement domes and basement highs will appear as gravity lows. The shale target horizons are conductive. You notice from just in general and from some of our other deposits. Make the point again here that we're going to miss those mobile hydrocarbon type of deposits, which don't have the same easy to detect signature. That's okay. We're undercover. we have to do the easy stuff, right? We're not going to complicate our lives by looking for something that doesn't have much of a geophysical signature. So do airborne EM to locate prospective areas, and the shales are also slightly magnetic due to their pyrrhotite content. This is the existing countrywide government gravity, which is a very good start. Based on our model, this is basement near the surface, this is deeper basin, and we would like to be somewhere here on the edge. Now, this is also where the iron formation is, where the junior was drilling, and so this is where we started our exploration. But let's look at the next one. We also had the government mag, which is actually very good quality over all of Botswana. This is the iron formation. We had to start somewhere. We started with this. We had a brave geologist, Jan Godfrey, who drew the first geology map based on this. Big structures, guesses at what was higher and lower stratigraphy and where the basement was. This is all about the relationships of the reducing horizons to the basement. And then we flew the airborne EM survey to map our redox boundaries. So a couple of things come out of this. First of all, these are the shale horizons, right? So we've flown this big area of 12,000 square kilometers, and we see that in fact this area I'm circling around is the interesting area in terms of what we can target with geophysics. And the other thing is we can see here these areas actually when you look at translate the EM, you invert it for depth of the more conductive Kalahari units over the basement. You get these areas, which are where the Kalahari sands are 100 meters or more. So we immediately discard these for exploration. Too deep to be of much economic interest, too hard to see through. So between, in these two images, what we've done is we've taken our 12,000 square kilometer area and we've immediately reduced it to actually less than 2,000 square kilometers of ground that we now want to explore. So we paid 1.2 million for the EM survey, which is a big upfront cost, but we got some immediate and tangible benefit out of it through our targeting focus. Not only do we get that, we also get some 3D geometry out of this. So here is a map of all the conductors that were picked on all the lines, and you can see it translates into a map colored by depth to the top of the shale, and dip, these little lines that stick out on one side or the other. So now, when you go around this, you see, now this is our interpreted basement for the moment, and you see that we've got dips going to the west here, dips going to the east here. So our shale horizon, we've been able to turn it into an antiform, and it immediately has a more perspective geometry with respect to the basement. All the way to the drill hole now. So this slide actually is illustrating the real difficulty in operating without that critical geochemical layer that we got so much out of in Zambia. What can we do now? So the ingredients, we've got basement, we've got reducing horizon and structure. So right now, at the time when this was done, we didn't yet have any geochemistry. And so the best we could do was to target reducing horizons in structurally, geometrically interesting expressions, right? So basically, we modeled these as you would, as EM plate models, and we drilled them. And indeed, we got to the shale within tens of meters of where it was modeled, but there was only trace chalcopyrite. So we really need that geochemical layer. Yeah. So a very expensive drilling program, 2-kilometer centers to go down to the Kalahari cover. This just shows how we can map the depth of cover with the EM. It's more complicated than just a single sand layer. We're doing all sorts of stuff down this 4-acid digest multi-element geochem aqua regia as well, followed by hydro sampling, carbon isotopes, carbon sachet for PG and gold, pH and EH, everything we can possibly do. It's a very expensive program, but as I showed in the previous slide, there's not that much more we can do without this critical geochemical layer. And these holes in green are the holes that we drilled that are down here, but the hydro program is being expanded to include sampling of cattle wells and government bores. Are we there yet? Well, it's a long road, and we're not there yet. As I said at the beginning, we don't have the prize to show at the end of the story, but this has been an illustration of the manner in which we're proceeding. We're taking our learnings from the Copperbelt and we're trying to apply them to basically one of the most difficult situations where you can't see anything at the surface. So some generic conclusions. I'm skipping any conclusions on sed-hosted copper itself, but about mineral systems undercover exploration. It really requires that you collect systematic and high-quality data sets of large aerial extents. One thing is you have to get outside of the footprint of your deposit. A small postage stamp right in the deposit that doesn't, you see, normal background is not very useful. You have to develop the model elements, so you have to know what to look for. And you know, there's an argument about model-driven exploration versus not, but any time, anything you do has some model elements to it. And you have to develop proxies to map these model elements by geophysics, geochemistry, mineralogy, some of the things I showed. And finally, basically, you have to have some staying power. This is not kind of exploration that you do in one season. Like maybe Tony was referring to in the past talk. This year you do nickel, next year you do graphite. Basically, pay the money, do the work, and stick with the program for a while. Thank you.
Thanks, Chris. Maybe one very quick question, or quick question, quick answer.
Why diamond drilling?
We wanted to have all the information possible, and maybe, you know, maybe we could have done otherwise. We're spending a lot of money. It was $15 million exploration program in the first year. We want to sample. We're sampling all down the hole. We want to get as much information as we can because we really don't know which horizons are most useful. Perhaps it is that we don't have to drill all the way to the Contagion rocks. We can sample higher up. But basically, that's the reason this is our Rolls-Royce exploration program so that we can do something cheaper and faster the next time.